Okay.
Call me.
I won't call you. I didn't bring my phone. Okay, don't worry. Okay. Okay. Thanks a lot.
Yes.
Yeah. Okay. Right. So last lecture I think we missed, and of course I took a holiday and everything. And today I was late because I was called for something, and we have some visitors and everything. Anyway, so just to recap, we covered a lot of stuff last lecture. Yeah, we went through the entire renormalization procedure at one shot. So I'll just recap a little bit here. Lecture 4. Again, we'll start LSM. I'll kinetic. So if you want to do renormalization, what you have to do, you have to choose a gauge, like in QED, you have to choose a gauge. And for non-abelian gauge series, you also have for fun, I wanted to write the full form of the Lagrangian, but it will take some time. Okay, a couple of pages or something essentially. Okay, those are required for non-abelian gauge series, quantization of non-abelian gauge series essentially. So now what happens at one loop? Everything gets mixed. So this goes here, this goes here, this gets here, this is here. So everything is fixed, and we choose the renormalization in something called RZ gauges. So again, just to recap, I know everybody knows about renormalization after the last class, but just for fun to revise, first step in any renormalization, let's just look at QED renormalization. First step is regularization. So we use dimensional regularization, DR. Okay, dimensional regularization to isolate the infinity another process of renormalization is called cutoff. So tomorrow you'll have one of the first examples, one of the first exercises is to use cutoff regularization for QED and derive the effective Lagrangian. One loop effective Lagrangian. This is sometimes not strictly also called Wilsonian approach, because he gave physical interpretation of renormalization of an effective Lagrangian derived with using a cutoff, essentially physical cutoff. Because otherwise regularization and renormalization looks really like some mathematical gimmickry. It doesn't say anything about what is the physics happening behind it. Wilson is the only guy who gave a complete physical picture behind it essentially. So he used cutoff, and we'll come to the problems of using the Wilsonian cutoff method for standard model essentially. Okay, we'll come to that point a little bit later. So the first step in any renormalization procedure is called regularization, where you isolate the infinity or introduce the infinity. The infinity as a momentum cutoff. You don't take the momentum all the way up to infinity as momentum cutoff lambda. To the second step is renormalization. Absorb the infinities into the parameters of the theory. So this is, I am using general renormalization theory here. Okay, the results from general renormalization theory. So you observe the infinities and the parameters. If the parameters are less compared to the number of independent infinities, such a theory is not renormable. So renormable theories are theories in which the number of possible infinities you get and the number of infinities you get and number of parameters in your theory should be equal to each other. Essentially, should be equal to each other. Okay, so you have mass renormalization in QED, electric charge renormalization, and wave function. So the three renormalizations we have in QED are mass, electric charge, and the wave function. And there are only three independent infinities in QED, which are essentially your vacuum polarization, okay, self energy, and vertex connection. Very good. We are going to, I am repeating this same thing again and again. I know it may be boring for some of you, but we are going to transport the entire same language also into this one. So you have vertex, self energies, and then what is the third one? Vacuum polarization. So we'll remember them in terms of graphs, much easier. We don't need this. So the three main graphs you should remember are this correction, and this correction. This is the self energy, this is vacuum polarization, this is the vertex correction. Now QCD, you have roughly the same thing except the complication that QED is the same thing. Okay, QCD is roughly the same thing except the only complication is it's a two complications for QCD. Is non-abelian. So there are ghosts. The second complication is coupling is large. Okay. So you have to take into consideration whenever you're computing QCD renormalizations, essentially all the strong coupling renormalization. Okay. You have to take into consideration the ghost contribution also put into the picture. Only then it will be the gauge invariant, any correction. Why do you want to put everything into this? Because you want everything to be gauge invariant. The final physical observables should always be gauge invariant. So the entire process of renormalization should make physical observables invariant and scheme independent. So what you measure in an experiment should be both gauge invariant and scheme independent. The schemes we have seen are two schemes. I mentioned them. I didn't introduce. I only told what are their properties. Essentially, one is on-shell scheme, one is the MS bar scheme. So the two schemes we know are OS, MS bar. Okay, so this all I think we mentioned it essentially. Yeah. That only happens in QED. It doesn't happen in general. QED is a very special case for the U1 case in which Z1 is equal to Z2 essentially. Right. 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 So, okay. So, in QED, what you can do, there was no general renormalization when it was done essentially. So, you can think of, they use graph theory techniques and Watt identities essentially to figure out how many, there is something called the Weinberg theorem which tells you that if you have a complicated process, okay, say at nth loop or something essentially, how many infinities at that order, how many infinities you can have, independent infinities you can have essentially. So you can always show that at a given order in perturbation theory, say one loop or two loop or something, you only have three independent infinities, any diagram you choose, and these three are the only three infinities you can have: vertex, self energy, and vacuum potential. There is no other graph, Feynman graph, which you can draw, which is cannot be renormalized by any of these three at a given order in perturbation. So let's say, okay, let me give you an example. Suppose if you have a two loop QED, okay, or some much more complicated. If you look at so this is two loop self energy. Okay, two loop self energy will only have essentially the graph. This graph can be renormalized at one loop level with one self energy. The other one will be, there will be no other infinity which will be, there is something called overlapping divergences, but that is a different issue. Okay, there is something called overlap divergences, but still if you renormalize at each order, one loop self energy and two loop, so you are asking if there could be some mixed sort of thing essentially. So there could be vacuum polarization within a self energy sort of thing. That is a possibility. Such diagrams are there, but independent infinities you can resort to classify them as only these three. So there won't be any other new infinities which are generated if you go order by order renormalizing these three. You can take any process, you can divide the infinity. So if you took at all two loop level process, say for E plus E minus going to me plus me minus, and you are computing two loop QED corrections to it, and the diagrams will be very complicated, but you can identify the sources of infinities as only coming from self energies at two loop, vertex at two loop, and vacuum polarization at two loop. Okay, there is a slight complication that there could be something called overlapping divergence. We will not get into it. There is something called overlapping divergences, but there are ways of getting rid of that. Yeah. So that is possible because QED is renormalizable at all orders. And the crucial proof, how do you can show it, as that these are the only three things. This requires this thing. All this, any Feynman graph of n vertices and something will only have one subgraph which has an infinity. Or okay, you can show that the all possible subgraphs can be divided into subgraphs which have only infinities in this particular fashion. Okay, the photon field, right? The gauge field doesn't get it gets renormalized in non-abelian gauge theories. It gets, okay, the self energy does it essentially. Yeah, QED case, it's not a free parameter in real sense, it's a gauge parameter. No, the field itself is a gauge parameter. There are corrections to it. It does get renormalized. That is considered in terms of the vacuum polarization. That is only renormalization. Not you mean to say the A mu itself. The field itself will not get renormalized because it's just a gauge parameter. It's always associated with it. A mu will not really get relied, but pi mu nu is there. The propagator gets renormalized. So this gets renormalized. Okay, but you don't treat A mu as a free parameter in real sense. It's not the parameter such which you can renormalize. It comes with the gauge. In fact, you can you can choose the gauge field to be itself as a gauge parameter. Okay, right? You can choose the gauge field itself. Now this is this is about QED. QCD. Non-abelian coupling is large. That's the only two things. So that means for matching with physical observables, many orders to be computed. So you have to match, many orders should be computed. It depends on the precision of the experiment. Okay. So that's going to be precisely my talk today. Actually, these all repeat essentially. Okay. Now for Q, what happens for weak interactions, which is actually the standard model. Now that is complicated. Weak interactions. So QCD is the same, weak interactions. Just one more thing is QCD. QCD, the main thing what runs is the alpha S runs. The running of the alpha S is a very, very important running because it's very large. Okay. At one loop, this is B3. So then there is B4, B3 at two loop, alpha S. So this is a beta function. So now the beta function has been known up to 5 loops. Okay, people have computed the beta function of the standard model. Now in QCD, normally you only have quarks and gluons coming into the loop essentially. Okay, that's all will come at any level essentially in perturbation theory. No, because weak interactions don't participate, the Higgs doesn't participate, WGs won't come. So this beta function is much simpler compared to say beta function of alpha 2. Okay, this is simple and this can be solved. One loop can be solved analytically, two loop and everything should be solved numerically. So given a scale, so which you know the measurement very well, say for example alpha S lambda QCD can be written in terms of alpha S, say at Q square is equal to mz square 1 minus alpha S 4 pi Q square is equal to mz square log the difference between the scale. So Q square is equal to mz square. I can just put in mz square by lambda. So if I know this QCD value at say mz square very well, I can derive what its value at very low scales. I can do the reverse also. Okay, I can do the reverse. I can run it. So if I know it at one scale, I can take it into another scale, which can be up or below. So for example, from this you can derive alpha QCD would be around 1 at lambda QCD, depending upon. This is just one group beta function. It can be solved analytically. Oh, there is a B3 here. Okay. 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 This is just a one loop beta function. And so when you are matching with experiment, you should also know at what scale this is you are doing the experiment at, essentially. At what scale you are doing this. So now this will play a role actually in many when you are computing any BSM physics with I'll tell some ideas of BSM physics in which this will play a big role essentially. So one of the questions is how can you go into a conformal field theories or something. So I told in one of the things that standard model can be scale invariant and everything. Can QCD be scale invariant? Meaning it can be conformal or something. How do you build conformal field theories of QCD? So you look for some. You can write a general beta function with n flavors and n colors, and solve for it when it becomes scale invariant essentially. Okay. So those are called Banks-Zaks point, and these days they are coming back again in terms of unparticles and conformal dark matter and so on, so essentially. Okay. A log is it should also be square. A log should not have any scale, right? Yeah. Okay. I'll try to show you a plot the measurements of QCD coupling constant. I don't think I'll find out. Let's look at this. Maybe and weak interactions. Without electroweak symmetry breaking, SU2 will be conformal. SU2 can be confined depending upon any non-abelian gauge field depending upon the number of colors and flavors. No, but in the standard model, the number of colors and flavors are fixed. So suppose if you take them as real numbers, okay, write a beta function in terms of real numbers and run this the beta function and check when it becomes confining. So there are some fixed points essentially at which it goes to some numbers. Okay. SU2 itself can be confining. For example, Sachin is working on SU2 matrix models. Okay, okay. So SU2 itself can be, but not in standard model. Not in standard model. Okay, not in standard model. Again, this is a toy model of QCD because full SU3 is much harder. So it's take 3 by 3. Okay, yeah. Instead of 8 by 8 matrices, you take 3 by 3. No, there are anti-quarks, right? Gauge bosons don't have antiparticles. No, antiparticles in the definition of charge. So you can have color, no? RB bar, BR bar. So if you remember how to get the gluon color structure, so it's 3 times 3 bar is equal to 1 plus 8. Okay, It is RB bar, BR bar. These give you 6 combinations, and 1 RR bar plus BB bar plus CC bar, GG bar. Okay. Right. Okay. So just you can think SU3 matrices as just SU2 written in 3 by 3 format with all possible combinations. Gelman matrices. Yeah. No, U1, yeah. In U1, you don't have antiparticles for gauge bosons, but there are electrons and positrons. For gauge bosons, you don't have antiparticles. In SU2, anyway, that doesn't make any sense to talk about antiparticles because you define them as antiparticles only in combination with U1 after SU2 is broken, because W plus and W minus are nothing to do with SU2, they are to do with U1, the QED remaining surviving gauge group. The QED, so SU2 cross U1 is broken to a linear combination of them survives as U1 electromagnetic plus Fermi theory. So there is this Fermi theory, okay, which is there essentially, and this U1 is there. Under this U1, there are W plus and W minus. Actually, all the particles in the broken phase of the Standard Model, W plus W minus. Okay. Okay, weak interactions. This is the most complicated renormalization. I know some of my friends will hate me saying this, but it's true. It's much more complicated than QCD. And here you choose a gauge, mostly worked in RZ gauges. Only spontaneously broken SU2 cross or non-abelian gauge theories. Now, when we read this, it doesn't make any sense in the sense this statement says, because the way we are taught and we are conditioned to think is that nature is always spontaneously broken. Okay, but there are various other ways of breaking symmetry. Okay, there are various other ways of breaking symmetry, and maybe in the next class itself we'll see one more way, which is called dynamical symmetry breaking. Okay, there are various and explicit symmetry breaking. Okay, so there is spontaneous symmetry breaking means only the ground state doesn't violate the symmetry. Okay, it is the only state which violates the symmetry. The rest of the states are. So we are always, for us, we think that symmetry breaking means it's always spontaneous, but it's not true. In fact, there are a lot of issues with spontaneous symmetry breaking, like I mentioned a few of them. Okay, so other ways of symmetry breaking are called now. Let me just mention a little bit so that you appreciate this point. In spontaneous symmetry breaking case, you still have the symmetry which is conserved. The symmetry is not broken. So it takes another form called BRST symmetries. Essentially, it is even in the broken phase, there is something which is protecting the gauge bosons, the gauge symmetry. The symmetry is still conserved essentially. It's not completely broken, and that is the reason why you have the gauge boson masses being protected. They cannot take any values they want. They cannot take any values they can. Okay, so sometimes these are called BRST symmetries. Essentially, there is something which is always protecting these things. Dynamical symmetry breaking means, like I said, initial meaning in spontaneous symmetry breaking, you need an initial potential, no, nice potential, which is fixed. So who gives you this potential? Okay, so somebody should be sitting there and giving you this potential. So you can ask this question. Okay, yeah, but so suppose if nobody is giving you this potential, the universe itself should dynamically generate, should have some interactions which will mimic what this potential is doing, which should mimic what this potential is doing. Those models are called dynamical symmetry breaking. This is supposed to be more natural, theoretically, but nature doesn't think other. That is true. Okay, nature prefers unnatural things, as we'll see. Maybe in the next class we'll see that the technicolor models are ruled out precisely by what we are looking at, essentially electroweak fission test. Okay, so technicolor, RS, Randall-Sundram models are also some sort of technicolor models. Okay, and there are newer versions of it called walking technicolor. Top color. So many of them variations are there. Most of them have Randall-Sundram. It is the Higgsless models are a version of Randall's technicolor models. Okay, let me. So if you take Randall-Sundram background and do not put the Higgs, okay, in the and put the standard model in the entire thing, and now break the symmetry essentially of SU2 cross U1 symmetry by choosing your boundary conditions on both sides of the brain different. So, okay, which so that they don't match and they break the symmetry. That is essentially technicolor, because I'll do it in when I come to this. Do this. So RS contains so there is something called a TV brain and a Planck brain, right? So there are two brains, tensions T1 and T2 essentially, and there is a warp factor in between essentially. Okay. So this is called the TeV brain, and then there is something called the Planck brain. So why the gravity becomes weak at this scale? Now you put in standard model on this in the bulk. So put all the fields, pi-dimensional fields. So L, E, Q, U, D, but don't put the Higgs. Now this is the 4 dimensions are fine. The 5th dimension has a boundary. So you have to choose your boundary conditions at the Planck scale and the scale. So it's like on a plane. It's called S1 by Z2. I'll come to that in minutes later. Essentially, it's like on a line. You have to choose your boundary conditions, and with the boundary conditions, you can break. This is like something called the Schwarzschild symmetry breaking, okay, which happens, and you can break the symmetry of the standard model, and this is you are breaking. Okay, there are very nice things you can do here actually. Okay, I'll one thing, break by boundary conditions. and this is equivalent to Technicolor. Okay. The other thing you can do, you can put the Higgs, because there is a gauge group here, and Higgs will be part of the scalar gauge group. So if you have, okay, I don't know, I'll get time to do this. This is called gauge Higgs unification. So if you take a mu in 5 dimensions, this has a mu 4 dimensions and a mu 5. Okay, and this fifth a5 x y x y, this fifth direction can be considered as a Higgs. This is called gauge Higgs unification. And when you break the symmetry, I told you Coleman-Weinberg mechanism, right? I think, in which you try to generate radiative corrections to make the mu negative. The same thing you can look at for here. So the Higgs is protected, and you can have a Coleman-Weinberg, but with all these extra particles in the loop in the extra dimensions. And this sort of works for some gauge symmetries. Okay. Anyway, so these are all variations of Technicolor. This is Technicolor. The reason is, again, gravity is weak, but here it gets reflected as a strongly coupled theory. Using, and you can understand it from ADF CFT point of view or any other ways essentially. So this is weak in 5 dimensions, but why it's weak in 4 dimensions, but it's things are weak here, but here they are very strong. So you don't have the Higgs, but you have a lot of condensates here, and these condensates are all strongly coupled. Okay, these condensates are strongly coupled, and this is exactly like what happens in Technicolor essentially. So that's the reason it's a reversion of Technicolor. So the basic idea is that there are dynamics which can break the symmetry. Okay, dynamics means some new interactions which are break the symmetry, or you break symmetry explicitly. I'll come to the second point again. So dynamics breaking symmetry is called dynamical symmetry breaking, and Susskind. Maybe there are many papers, Cyber written. So there are many things which you can, okay, then Chivukula's reference. Susskind's paper is influential, you can read this paper. Then Weinberg's. This is sufficient to get the central idea. Then rest are all details. The other paper, the main paper is by Susskind and Weinberg, essentially, where he quotes Wilsonian methods and everything. Okay, Weinberg's and Suskind's paper are influential. You'll get the central idea because they are extremely clear, very nice. Rest of them you can read whenever you want. Now, what is, so this is, you don't have, the point is that this is similar to, we'll come back to this in a little bit later, which a version of this is like what happens with pion in QCD breaking. Actually, that is a much better one for composite Higgs. Okay, this is not purely composite Higgs. It's like the Higgs has interactions, new interactions, and Higgs is a composite, and there are multiple composites. Okay, so there is a new, here is new interactions, colored in the sense strong interactions, lead to the symmetry breaking. New strong interactions need to remove. So this is a completely different setup. So you can make symmetry breaking by this also. The other way of making symmetry breaking is, you say, I don't care about spontaneous symmetry breaking, I don't care about explicit symmetry breaking, I'll just write the terms in the Lagrangian and forget about it. That's called explicit symmetry breaking. But explicit symmetry breaking theories are not renunciable. So if you just start by saying in the broken phase, I'll just write the mass terms. Okay, I don't care how the symmetry is broken, but I know the symmetry is broken and it gives you the mass. In any model, these are non-renorms. In general, that means if you consider radiative corrections, that theory is maybe not be correct. So, so if you have small symmetries, say for example, I don't know of any cases immediately, but you can, if you have things like, say for example, if you have only scalar interactions, not gauge interactions, non-abelian gauge interactions or something. If you have only scalar interactions and some symmetry like Z2 symmetry or something, if you add a linear term, it breaks the Z2 symmetry, or a cubic term or something. It's explicit symmetry breaking. Okay, most of these types are not they are not very harmful. Okay, you are still breaking a symmetry explicitly, okay, not spontaneously, but they are not harmful because you are breaking them with terms which are dimensionful, okay, and so they are not harmful in the sense, almost mimic spontaneous symmetry breaking. When you break spontaneously, what happens is all the mass terms generated and all the terms which are generated are so-called soft symmetry breaking terms. Okay, that is important actually. So we will see many examples. So when you break explicitly, you are directly writing something called hard terms. So hard terms are essentially dimension-less coupling constants and non-renormable terms. Okay, and soft terms are dimension full coupling constants. Okay, and these are the ones which are soft symmetry breaking terms. So in view of this kind of breaking, spontaneous symmetry breaking is much more advantageous and it's renormable. Okay, and we'll see its features later on. Essentially, we'll see the problems with it later on. So in all this view, spontaneous symmetry breaking is preferable and its best choice. Okay, now this the first renormalization of standard model was done in non-shell scheme by Sirlin and Marciano, that group, in the light of the left experiment. Yeah, like I said, the renormalization of standard model is much more complicated. Till now, only some parts of the renormalization are done at 2 loop. Now I'm telling that QCD you can do 5 loop calculations and everything essentially, but standard model, not all particles, meaning all the calculations can be done at higher loops because we still don't have all the techniques to solve 2 loop diagrams perfectly. Okay, with massive particles. With massless particles you have. Okay, with massive particles, 2 loop, depending upon the graph and everything, it is a complete mathematical journey essentially. It's completely complicated. There are various techniques and it involves number theory, differential geometry, all kinds of things. So, most of it is done numerically, but even to do numerically, you should know the algorithm to do. Okay, yeah, okay. And the diagrams are so. Okay, so for example, alpha EM, including SM corrections, not QED, has been done by Degrassi et al. Only recently. Sirlin and Marciano, Langacker, Holick, so, for example, Sirlin started renormalization with Fermi theory. So, he started first corrections of GF, okay, in 1950s, and then by 80s he could reach the standard model renormalization. Okay, 30 years. Okay, one renormalization. Okay, okay, Marciano and Sirlin. Okay, and of course you know. Uh, the story of the Japanese guy who does phi loop G minus 2 of QED corrections, right? Essentially, you know, this G minus 2 QED corrections, you know. There is this Japanese guy who was a collaborator of Sirlin and also with Feynman, who computes, he is now 88 or 89 or something, essentially. Just missing his name, actually. He was in Cornell, okay. His main aim in life is to compute the QED corrections at higher and higher loops in QED for G minus 2 of the electron. What is his name? God. His name starts with T. Yeah, not Tomonaga, not Tomonaga. What is it? It's something similar, essentially. You should read his articles, essentially. His interactions with Feynman, and after he did 2-loop calculations for the G minus 2 in QED, and then 3-loop calculations, 4-loop, they found a mistake in 4-loop, and they published it, essentially. And 5-loop, they have partial results, actually. And now he is 88 or 90 or something like that. I'm missing his name. He and Sirlin wrote the first renormalization of Fermi coupled constant, 1950s. Now, oh God, I'm blocked. Okay, I'm just forgetting his name. Okay, now this guy is, nobody can check his results also. Okay, he's the only guy in the world who's doing these calculations. Okay, and he and his 3-4 people maybe. Now, yeah, that is the situation of the thing. Now, G minus 2 is required that we need 5-loop corrections and everything, and you have to see it. And pardon? Konishi. Kinoshita, yes, Kinoshita. His first name starts with T. Kinoshita. There is this, in QED, there is also this theorem, Kinoshita, KLM theorem. So, Kinoshita, Lee, Nyberg theorem. Anyway, so the point is that you can say I can calculate for any observable in standard model, right? 1-loop corrections. So you have many things. You can calculate for the mass of the electron. So what? But mass of the electron, mass of the Higgs, mass of the thing. You can start doing all kinds of things because everything is exchanged. But they focused only on one particular sector, which is the gauge sector, which was being probed at LEP. So in the 70s, the LEP experiment proposal was done. So it was needed that it was accepted, and they started building it and everything. So theorists had to start working for LEP, meaning, so they had to do something to calculate, because they knew it's an E plus E minus collider at a very high end. I'll tell you more about it. I'm already running late. Okay, yeah. Okay, so what precision or what observables to calculate at higher order. And this is set by the experiment. Now you can do the full renormalization of the standard model and calculate whatever you want. Okay, but then who will measure what? Nobody will measure anything, right? So depending upon the experiment, you choose your observables. So this entire set of observables was given a lot of impetus by the construction of the LEP experiment. Now, the LEP experiment, I am emphasizing it so much because even today this data is much more relevant because there is nothing which is so precise even at LHC. There is nothing. The mass of the W will come close at LHC slightly. There is a measurement of mass of the W essentially, which is slightly more precise at. But none of these observables, they have a very what do you call, they are sort of, these measurements are rock solid, they are at that particular energy, and they have very strong implication if you want to modify especially the gauge sector of the standard. If you want to modify how the electroweak symmetry is broken in the standard model, because as I said, it should be only spontaneously be broken. If it is not broken spontaneously, what happens? And those constraints are ruled out only by experiment. They cannot be done by theorists. Theorists can, it's a playground of ideas essentially, and this experiment essentially was the one which played a very important role. So what is the key idea of a LEP? LEP is an E plus C minus collider. I'll show you more slides on it essentially. And this can go into gamma. Now until then there was no interference between gamma and Z, meaning there was no energy to really produce the Z essentially. So the point essentially that you need root S close to twice the mass of mz is the point essentially, so that you can really push it. So here you can have hadrons, leptons, and all kinds of leptons. Except top quark, all the hadrons will be produced essentially. The main thing which can be produced is the bottom quark essentially. So it started with root S around 100 GeV all the way up to 200. It barely missed the Higgs boson by 15 GeV essentially. Now, so what is the theory for this LEP essentially? So maybe I'll just show you the LEP. Oh, what should I do? Yeah. So maybe I won't have time to show the slides today, but anyway, I'll show it next time. And then I'll also talk about technical research. Okay. So let's do some theory part of this. Like I said, this experiment was focused on this particular thing. So earlier, so what is the most crucial thing about the mixing of gamma and Z is essentially what is it, because both of them are neutral gauge bosons. Okay, and the thing which makes a huge difference is the presence of gamma is not parity violating, Z is parity violating. Okay, that's the main thing. If there is an interference. Okay, earlier people were measuring this from neutrino scattering. One of the first measurements of this gave an indication on sin square theta w. So sin square theta w is the one which mixes G and G prime. Okay, it is the one which mixes G and G prime. So I think yesterday Tarak was talking about sin square theta w. Okay, the oldest experiments essentially measuring these things. There were many. One of them was called Newton. Lot of errors. So it had a higher value of sin square theta w compared to other places. So sin square theta w should be around close to 0.3. But if you want precision, you can go up to about few percent of this value. So neutrino scattering on hadrons gave a value of wherever I think Gargamella experiment was covered by Nirmal, right? Gargamella experiment. Gargamella experiment is the place. It is a fantastic experiment. Okay, it is a place which was built for something else, and they found neutral currents. So the first discovery of neutral currents happened in 1977. I don't have those slides, or maybe they have. Okay, I'll show you. Yeah. So that Gargamella experiment. Let me see if I have those slides. Where they first discovered. Okay. They first discovered experiment. Okay. No, I don't have them, and I'll see them. Okay. They discovered. So in the old days, what was neutrino physics was this. There is a very nice article of Georgi on it's called neutrino physics. Okay. What it means is you scatter neutrinos on hadrons. Now, why neutrinos on hadrons? Now, neutrinos can only interact with leptons with charge current. Okay, with hadrons they can only interact with neutral currents. Okay, so the neutrino diagrams, if you remember in standard model, E is W. Now W can go to something else, QQ prime or top bottom or whatever it is. But if you want to have interact with, you don't want electron in the final state, but instead you want a neutrino in the final state. This will only be through a neutral current. Okay, so if you measure the electrons, you know what is all the charge current part. When you bombard the neutrinos with some, okay, you measure all the electrons. Okay, and if there is nothing else, this gives you the charge current component. This gives you the neutral current component. So measuring the charge current and isolating total cross section, Measuring the total cross section, isolating the charge current will give you the neutral current component, and this is how the discovery of the neutral current was done. Okay, so you have charge current interaction, neutrino interacting with this thing will be through a W. This is the same thing even in any neutrino physics. Oh yes. Okay, sorry. Yeah. Okay, yes. Okay. So if you measure all the charged particles in the final state, whatever, if your electron comes out, you know what it is essentially. So you know that you can isolate the charge current process, and the remaining one would be only the neutral current component. And if you know the total cross section, okay, if you know the total cross section, isolate the electron charge part, essentially you get the charge current component. You won't see the neutrinos anyway. You won't see the neutrinos until phasor and SND. There is no collider experiment where you can see the neutrinos. Okay. So this is how they discovered neutral current process, and this is where they estimated sin square theta W, the neutral component by the charge. Now these were to be measured at a higher level. So the first things you have to do is calculate radiative corrections to sin square theta W. Okay. Anyway, since I started experiments, let me show. I'll do the reverse. Oh, which one? Which one?
Which those switches, the mains that. Yeah.
Oh, this is for both the things. Okay. Oh God. Very bad. So this is on. That's what happens in snow. They could actually measure the charge current component and neutral current component. It's a neutral current component. That is a snow experiment. So electron neutrinos which are coming from sun, they get converted, half of them, to mu and tau. So if you measure the neutral current component, you can see the rest remaining missed part. Okay, they don't have charge current interaction in the detector. Okay, so nu mu and nu tau also will contribute essentially. Pardon? No, snow has two things. Yeah, snow. Pardon? No. That's not that way. Essentially, snow is not vibration of the nucleus and everything. So snow is essentially dissociation of deuterium and tritium. Essentially, two things. Snow has two things. One is dissociation of deuterium because it has heavy water essentially. Oh, okay. And then the other one is electron scattering on electrons. Okay, so we are starting with the experiment today essentially. So this is the snow. This is the okay. Okay, all right. Okay, this is the lab result essentially. The lab experiment. It's remember that it's the same tunnel as LHC. Okay, it's the same tunnel as LHC, but it started much late, even before I was in school. I mean, I was coming out of school or something. So okay, and then it had 4 experiments: L3, Delphi, Opal, and LF. Almost similar, like in uh, uh, LHC. So it has a proton source and 2 rings, PS and SPS. These were PPE rings. Earlier they were PP rings. So this is where essentially SPS was the where Carlo Rubio won Nobel Prize for discovering WNC. Okay, and okay, rest of it, this is yes, that was the old 83 result of Carlo Rubio. So this was the ring corresponds to SPS. So they had experiments UA1, UA2, which discovered W and Z. There were 2 experiments, UA1, UA2, which discovered W and Z. In addition to this ring, there was a big ring dug only for sun. And then they had to calibrate this ring because they were doing high precision experiments. So they had to take care of all kinds of effects, like a train moving. You must have heard about this thing, right? Yeah, all these stories. Electricity in Geneva city, all kinds of things. Okay. So this is between France and Switzerland, and so these 4 experiments. So they ran with center of mass energies around 93, 94, 95 with integrated luminosity. Now these integrated luminosities looks very small compared to what do you call LHC has. Now this is the point. The main thing was that they want to sit at the Z pole. Okay, so now you see the cross section on the y-axis and the center of mass energy. You see that it's really sat on, okay, something which is exactly at the Z mass, and then the number of the cross section shoots up. How many orders of magnitude? At least 3 orders of magnitude. And then it went down to center of mass energies of this 220. So these measurements, which happened at Z pole, are essentially important, which are called which were called the Z pole measurements, which were called the electroweak measurements. These are the ones which made it. Okay. The subsequent measurements happened much later, and it ran up to 2000 or something, 2001, 2000. And they tried to run it for a couple of more years. Okay, so this point where the center of mass energy matches with the Z mass around 91.2 GeV is the main measurements, where they measured a lot of measurements. They produced about 1 million Z events. Pardon? No, Higgs requires much more masses. 1 second. Hello? Yes? E2 912 ಅಲ್ಲಿ ಇದೆ, OTP ಇದೆ, ಅದು ಅಲ್ಲಿ ಮೈ ವೈಫ್ ಇದೆ. ಓಕೆ, ಹೇಳಿದ್ರಿ OTP. ఓకే, నేను చూస్తాను, ఒక్క నిమిషం. Okay, so what it measures? So it is sensitive to self energies of the Z boson. Okay, it is sensitive to self energies of the Z boson, So what you have, gamma Z mixture essentially, and the loops with FF bar, with the Higgs, and W and C. Okay, so because you're measuring it at very precisely with millions of events around that scale, essentially I'll show you the number of events. So it is sensitive to these self-energetic diagrams, okay, which are measured at two different energy scales, one at the Z pole and also at Q square is equal to 0 essentially. We'll see. Okay. Now, one of the main things where they can measure is called sin square theta W, which I mentioned essentially, which is measured by something called forward backward asymmetry. So, is there an asymmetry if you are moving forward in direction or in the collision direction axis and backward direction? Okay. So, why there should be an asymmetry? Because it will be because of parity violation, gamma phi, which compares here, and they could measure sin square theta W much precise compared to any other experiment in those times. And then they also measured the width of the gamma and the width of the gamma Z in various decay final states. Gamma Z hadronic, gamma Z leptonic, in leptonic gamma Z BB bar. In all of these things they could measure extremely precisely because they have a lot of B events and it's a very easy experiment to do essentially. Oh God, I don't have my phone. I don't. Hello. ಒಂದು ನಿಮಿಷ ನಾನು ಹೇಳ್ತೀನಿ. Okay. Yeah. I didn't bring my phone. I don't know how to do this now here. Okay. Yeah. Now this is very famous. What is the width? Width is the lifetime of the particle. Width is just 1 by lifetime. Okay. Now the most important, of course, which we all are interested in essentially is the invisible decay width of the Higgs. Okay. So the invisible decay width is fantastically measured. Okay. And so it has 2 neutrinos or 3 neutrinos or 4 neutrinos, and it could tell you that there are only 3 neutrinos. Okay, this is highly precise. So you see the error bars in this, very small. It doesn't fit 2 neutrinos, it doesn't fit 4 neutrinos, it only fit 2 neutrinos. Now if we get something similar for the Higgs, we can have Higgs mediated dark matters and all that stuff essentially. And if you have an extra Z prime, you can have constraints on this, the invisible decay. If you have any particle which connects also to the Higgs dark matter, which you'll also have constraints on the invisible decay of it. So the Higgs decay width is invisible decay width is really very strong. Okay, very strong constraints, and these are the measurements by the 4 different experiments, and this is a chi-square fit essentially. Now see the error bars, they are at 1% level. So that's the reason why we need radiative corrections. So this is mz, this is gamma g, it's about 2.5 GeV inverse, the width of the Z essentially. Hadronic cross section, I'll introduce all these particles, forward backward asymmetry with house, bottoms and various things. This set is called the electroweak precision test. Okay. No, not only this, but if you do a global analysis from the left, if you do a global analysis, you collect other experiment results. Sometimes you also put atomic parity violation experiments and everything. Okay, but these are So there is a there is a global analysis comparing with all the 4 experiments essentially, LF, Delphi, Opal, and L3. India was involved in L3. TFR was involved in L3. So you see these numbers and you see the precision. Okay, at what level you are measuring. So you can. They also give something called the pull diagrams, which you must have heard for each observable. So, for example, MZ, what is the pull from various experiments essentially? What is the from the central value of doing a global fit? You also have how many sigma away you have the rest of the experiments. Okay, so each this yellow band is 1 sigma. Okay, how many sigma away the central value is from the other experiment. So you have gamma z, mz, rl, sigma 0 hadronic. This sigma 0 hadronic also goes into the calculation of sin square theta w. Calculation of sin square. Now, to do a global analysis, there are 2 main popular codes which are called Z-fitter and Z-fitter. They are computing actually analysis which do this electroweak precision. It's complicated essentially. One of them has closed down essentially. It's not updating. So these things can be used, but there is an easier way of doing your own. If you have a new model, say for example, okay, you can now actually calculate the electroweak precision measurements in much. There is a slightly different way given by Wells and Kang essentially, which can do the. We used it in one of our papers, and we can actually calculate the chi-square fit for the electroweak precision measurements. So the people in understanding these people are essentially Barberi and company, and who did all these measurements essentially. Measurement is not matching in the sense these are different experiments. Say for example, there are all these are the pull. So the central value, which one? This one, Delphi. Which one? This one, yes. Delphi, that one, essentially, gamma zero. That's fine because it could be its own systematics. So that's the reason why we have 4 experiments. Each experiment will, that's the reason we do a global analysis to put in the best. So this is the global analysis of all the 4 experiments, and this came out in 2005 or something. 2005, much later, after LEP closed down 4-5 years much. Okay, it's a physics reports. You can look into it. Yeah. Now, so the main takeaways are these measurements, and of course this one, the invisible width of the Z, and these measurements. Now we have to match with theory. How the standard model fits. Okay, I'll stop now. Okay, I have too many phone calls to attend. Okay, all right. Okay, and then next week we'll look at how to fit the standard model into this, and look at first BSM model, which will fix mostly something called STU parameters. Not next week, Thursday. Sorry. Okay, and how the technicolor kills it, killed by the technicolor. I can put it on Teams.